Hello guys, and welcome to another calculus video. In this video we are going to be solving this very nice integral that you can see on screen. It comes from a Stack Exchange post, so thank you to the poster very much because I really enjoyed solving this problem. I think it's an excellent demonstration of how the hardest part of calculus is by far the algebra. It's not the calculus. And this is definitely a special case of that because you just gotta think back to Algebra 2 and all the strategies you used in that class to solve this one. So let's go ahead and go over the lemmas that we're going to need. First of all, we're going to be using the definition of inverse hyperbolic tangent of x, which is 1/2 natural log 1 plus x over 1 minus x. We're going to be using a lemma that I proved in a previous video, the integral from 0 to infinity of x to the n over hyperbolic sine of x dx equals 2n factorial times 1 minus 2 to the negative n plus 1, all multiplied by zeta of 2n plus 1, or of n plus 1, sorry about that. And also a quick lemma that we're going to prove right here. The integral from 0 to 1 of natural log to the n of 1 minus x over x dx is going to be negative 1 to the n times n factorial times zeta of n plus 1. And to prove that super quick, we make a quick substitution replacing x with 1 minus x, and this leads us to this nice expression. Then we expand 1 minus x as a power series, so it's going to end up looking like this. Then we just have to do some quick stuff right here. So if we have the integral from 0 to 1 of x to the k dx, it's just going to be 1 over k plus 1, right? Then when we differentiate with respect to k, we're going to get an ln x out of that, and then we differentiate the other side, and it's going to become negative 1 over k plus 1 squared. And we can repeat this process n times, differentiating n times, and eventually what you're going to end up with is just a nice little recurrence relation, and you're going to end up with the integral from 0 to 1 of x to the k ln x all raised to the n power dx is going to be negative 1 to the n times n factorial over k plus 1 to the n plus 1. So taking this expression right here and applying this formula right here, we get the sum from k equals 0 to infinity of negative 1 to the n times n factorial over k plus 1 to the n plus 1, which is just a representation of the zeta function. So we have negative 1 to the n times n factorial times zeta of n plus 1. So that's a quick little lemma that we're going to use. So let's go ahead and jump right into the problem. So first thing with this problem is something that I actually want you guys to try and figure out for yourselves, because of course the whole point of solving all these cool problems is so that you guys can figure them out by yourselves and learn more about problem solving skills and stuff like that. So I want you to notice here that we have natural log squared of 1 plus x, natural log squared of 1 plus x, and natural log squared of 1 minus x. And if we add up the powers as if we were going to multiply this all out, we find that it's all on the order of 4. So order of 2 natural log 1 plus x, order of 2 natural log 1 plus x, and order of 2 natural log 1 minus x. So if we were to multiply this out, it would all have a power of 4 in terms of natural logs. Also, you'll notice that I've underlined this 6 right here, and the reason I put this here is because whenever you see a weird number that doesn't really match with anything else in the integrand, that number is typically going to be there for a reason. They didn't usually put some random constant in there just to throw you off. And so the question that we have to make here is, what is the connection between 6 and, oh my god, you're kidding me. It says 6 and 5. It should say 6 and 4. Between 6 and 4. So what's the connection between a coefficient of 6 and a power of 4? I'll go ahead and give you a minute or so to think about that, because that's really the key to figuring out how to solve this problem. Where do you see a power of 6 and a coefficient of 4? If you were able to figure that out, which hopefully you were, what we're actually looking at here is the binomial expansion of a plus b to the 4th power. Now notice here we have a plus b to the 4th power. We're going to get a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. And notice that this a to the 4th lines up with our 4th power, and then we have this squared and squared, which is similar to natural log squared of 1 plus x times natural log squared of 1 minus x. So let's go ahead and let a equal natural log of 1 minus x and b equal natural log of 1 plus x. We're going to define a separate integral I naught, which is going to be the integral from 0 to 1 of natural log of 1 plus x plus natural log of 1, natural log of 1 minus x plus natural log of 1 plus x all raised to the 4th power over x dx. Then we just go ahead and expand everything out. This is a really huge expansion, and I did do it out of order here. So first we have natural log 1 minus x to the 4th power, which we'll take as I1. Remember that there's an x on the bottom here, and we're integrating from 0 to 1. Then these terms with the 4's are going to be I2. We have natural log cubed of 1 minus x, and natural log 1 plus x, and natural log of 1 minus x times natural log cubed of 1 plus x. And then the remaining terms are these natural log to the 4th of 1 plus x and this 6 natural log squared term, and this was just our original integral I. So overall, we have that I naught is equal to I1 plus I2 plus I. Let's go ahead and solve for I naught, I1, and I2. So for I naught, notice that we have this nice little natural log of 1 minus x squared, which is a lot easier to deal with than natural log of 1 minus x times natural log of 1 plus x. And so all we have to do here is substitute u equals x squared, and we end up with this nice expression. And then using the formula that we derived at the beginning, we arrive at the fact that this integral is just equal to 12 zeta of 5. Then I1 is almost the same exact integral, it's just missing that squared, and so we end up just getting 24 zeta of 5, just using the same exact formula. Then I2 is a little bit more interesting because we get to use some more fun little tricks. First of all, we're going to just go ahead and factor everything. So we're going to factor out 4 natural log 1 plus x, natural log 1 minus x out of everything, and we're going to end up with these 2 natural log squares adding to each other. And now we do some other cool tricks right here. So I know this may seem a little bit out of the blue, but this is actually a relatively common trick when you have something that looks like a squared plus b squared, or you have something that looks like ab. And that's if we analyze the expansion of a plus b squared, we notice that the only difference between a plus b squared and a minus b squared is that we have plus 2ab or minus 2ab. And what this means is that on the left side here, if we add a plus b squared plus a minus b squared, we just get 2 times a squared plus b squared. And then if we get a plus b squared minus a minus b squared, then we just end up with 4ab. And the reason we're trying to look at these expressions here is because when you have natural logs that are multiplied by each other, they're incredibly hard to deal with because that's just not the way that natural logs like to work. But when you have natural logs added to each other, they sometimes have really nice forms. So for example, since in this case our a and b are natural log 1 plus x and natural log 1 minus x, when we add them together we get natural log 1 minus x squared, which is just one natural log rather than 2. And when we subtract them, we get 2 times the inverse hyperbolic tangent of x, which is a little bit nicer than some natural logs because we have some tricks with the inverse hyperbolic tangent, right? So what we're going to do here is we're going to match up this 4ab with this 4ab right here. And we're going to match up this a squared plus b squared with this a squared plus b squared right here. And so what we end up with is the integral of 1/2 ln squared 1 minus x squared minus 4 inverse hyperbolic tangent squared of x. And then the same thing with a plus sign. So we have a minus sign and a plus sign and two things that are squared, and the same two terms on either side, so we can go ahead and use difference of squares. And we end up with 1/2 integral from 0 to 1 of ln to the 4th of 1 minus x squared all over x dx. Reminder that this is I2 that we're calculating right now. And this can be calculated, I believe we already calculated this, but anyway, you just use the same steps and the same formula that we used before, and you get 6 zeta of 5. And then for this other one right here, which I'm just going to go ahead and call I3 just to make things a little bit easier. With I3, we have this inverse hyperbolic tangent, so of course we're just going to substitute x equals hyperbolic tangent of v. Then dx is going to be hyperbolic secant squared of v, dv. And so we end up with 8 times v to the 4th hyperbolic secant squared of v over hyperbolic tangent of v, and when we reorganize, we just end up getting hyperbolic sine times hyperbolic cosine on the bottom. Then, using our hyperbolic trig identities, we know that 2 times hyperbolic sine of v times hyperbolic cosine of v is just going to be hyperbolic sine of 2v. So we go ahead and apply that. Then we let 2v equal u, we factor out all our constants, and we end up with the integral from 0 to infinity of u to the 4th over hyperbolic sine of u du. And then applying the formula that I showed at the beginning of the video, which I derived in a different video, just plugging in everything, and we get 93 over 4 zeta of 5. So now let's go ahead and plug everything in. Remember that our original formula was I naught equals I1 plus I2 plus I. I naught was equal to 12 zeta of 5, I1 was equal to 24 zeta of 5, I2 was equal to 6 zeta of 5 minus I3, which was 93 fourths zeta of 5, and then adding I, And now, in my opinion, is the absolute hardest and most complicated part of the problem, which is simplifying all the fractions here, because honestly, I cannot tell you how many times I screwed up trying to simplify the fractions. It was a little bit embarrassing. So I'll leave that up to the reader just because I can't show the proof because it's a little bit too long to fit in the margin here, if you know what I'm saying. And so once you've fixed all those fractions, you get I is equal to 21/4 times zeta of 5. So I hope you guys enjoyed this short little video on an interesting little problem that really required a lot more algebra and binomial theorem than it did calculus. So thanks for watching, and I hope you enjoyed. See you next time.